Okay, thank you very much for coming in such a great number to this joint Pure and Applied seminar. I'm here as the host, and I should introduce Mark Hooker, which is a little bit ridiculous since I've been only here 1 year. But I'll say a few words about him. So Mark did his first degree in mathematics at Oxford University. And after a year in the industry, he wrote his PhD on nonlinear waves at Bristol University. Afterwards, he did his postdoc work on wave impact with Howard Peregrine. In 1992, he joined UEA, that's 30 years ago. And over 29 years, he taught many service courses to students in other schools, as well as a wide range of applied modules in maths. His research continued on liquid splashes, sea wave impacts, and other violent flows. He often collaborated with engineers. Some of the pure mathematicians might be shocked about that. In the 90s, he did experiments and developed a theory of waves fully interacting with moving containers. This work was revived by collaborators at c.AD University. He retired in 2021, but he continues to pursue his interest in applied mathematics as a visitor here at mathematics. He always held a fascination with the history of ideas in exact science, from antiquity up to the modern era. And so now he's going to talk to us why study the history of mathematics. Thank you very much, Mark, for agreeing to give this presentation.
Thank you, Alberto. Thank you for the introduction. Thank you, everyone, for coming. I'm really touched that you are coming to my talk. And I'm going to try to address this question, why study the history of mathematics? I'm partly going to address skeptics in the audience, or people who have no interest at all in the history of ideas. I hope to persuade you in the next 45 minutes that there's something in this. Some slides I'm going to just quickly slide over because time is quite pressing and I have a lot of material. I am my own enemy for liking digressing, so I must not digress on the material I prepared for you. So this is an outline of the talk. It's not actually as long as this list. Most of the talk is going to be devoted to topic 1 about Alexandria, the library there, and topic 2, which will be about perspective. I have one equation in the entire talk, just one, but it's a good one, I think. Quickly, I have a list of sources so that you can rest assured that I really have spent a lifetime reading around this subject. And the book that I want to highlight here is the one in the middle, Ute Marsbach and C.D. Boyer. This is now in their 3rd edition, their General History of Mathematics. If you only own one book on the history of maths, I recommend this one. It was a gift from my elder brother when I was 18, and it completely transformed my view of mathematics and got me really interested in the history of ideas and history generally. The others I will glide over as more scholarly texts, but all very good. So this is about 2% of my reading of the history of maths. We do history of maths, point of pride that the school offers the history of maths for 30 years. I was involved for 7 years, and now it's in the very capable hands of Christina Christe. In the past, it's been lectured by 3 lecturers in any year, or 2, or 1 as it is now. I won't dwell on the details, except depending on the lecturer, it's covered a great wide range of cultures and back histories, different topics depending on the interests of the lecturer. And one of the big themes about history generally, as well as history of maths, is to decolonize the subject of history, meaning not just to spend time on modern Western view of things, but there's a whole world out there and every culture has contributed to mathematics. Just a little bit on this slide, which is about assessment. I prepared these slides for Surrey, where they don't have any history, so that's why I'm going over them rather quickly. I just want to highlight, you all know about history of maths here, but one thing I wanted to focus on again, because over the years that we've had it, every year we've been offering history of maths, and benefits to students at the bottom of my slide here consist of critical reading, reading carefully the original sources of mathematics. It's a good thing. Narrative writing, writing essays. Where else can they do that, really, outside of projects within their maths degrees? Developing some curiosity, and I hope to foster a bit more curiosity today about the past, and how to be skeptical about sources, especially when they're online. There's a lot of rubbish about history and history of maths online. It's good for students to know when it's good and when it's not so good, and when they can cite it in support of their thesis. So I'm now getting a bit closer to what I really want to talk about today. So this is a kind of summary of what I want to do. And I want to begin with Hilary Mantel, famous for her fictional writing about history. And she had this nice quote: "Evidence is always partial, and history is not the past. It is a method we have evolved of organizing our ignorance of the past." So I take the same view as others, that we have more gaps in the documented history of mathematics. You have to use some imagination to try to fill in some of these gaps. What can you do if you're going to write about history at all? And a couple of questions I want to address under the general title of this talk. What were the historical contexts in which mathematical research was done in the past? Where was it similar today? Where was it different? And I have a case study for that. And the second question is, how were ideas transmitted over space and through time from one researcher to others? Nowadays, it's difficult enough to get your wonderful paper noticed by fellow researchers. Think how much more difficult it was in ancient Greece, when everything was done in manuscript, and largely it was through personal contact that you could transmit new ideas. And ideas were lost, more frequently lost than remembered. So I got to talk about that in the second part, inventing and reinventing ideas over centuries of time. So in particular, the case studies I'm going to address to try and answer these questions are to do with the Library of Alexandria in northern Egypt, and the second one for part 2 is on transmissions of ideas to do with perspective and painting from the Renaissance onwards. We're going to be spending a lot of time in Africa, in Egypt, and I'm going to try to convey to you some idea about the city of Alexandria. And to explain the city of Alexandria, I need to go back a step and explain why Alexandria was founded. So this slide is about Alexander the Great, Macedonian general who conquered an entire empire to the east of Greece in his short life, 355 to 323 BCE, before the Common Era. And there's one story about him that he was given as a youth a jeweled cask which contained Homer's works as rolls, and he took the casket with him on his campaigns. After Alexander died at the age of, I think, 32, his remains were brought by one of his generals, Ptolemy, from Babylon, where he died, to Alexandria in northern Egypt. And this was a city which had earlier been founded by Alexander the Great when he was conquering that kingdom. And to continue with the anecdote, the embalmed body was displayed in a golden coffin with a crystal window for visitors to see. And it was later, sometime in about 300 AD, that's 600 years after his death, that the gold coffin was lost in some riots, along with other things that were lost at that time. So here's some of the background of Alexander the Great and the founding of the city of Alexandria. The Library of Alexandria was founded by one of Alexander's generals. So Ptolemy is a name that was continued for, I think, 12 generations through to the time of Cleopatra. And King Ptolemy I of Egypt and his successors had unlimited wealth. So that's something to dwell upon. If you have unlimited wealth, access to gold, and people willing to work for you, then it's just down to your imagination what you want to spend your money on. All the power and wealth of Egypt was at his fingertips and his successors' fingertips. So they come up with this idea of making a library which would have effectively no limits. It would contain all knowledge in all languages, though principally Greek language. It may have been founded to outdo the existing library at Pergamum, which, to give you a geographical setting, is now what we now call Turkey. And in that library, there were at least 200,000 parchment rolls at that time. And the collection grew so large in Alexandria that it spread across many buildings. I'll come back to these buildings: the Museum, the Serapeum, and the Royal Palace. The Museum, it's not a misspelling, that's a temple to the Muses, and the Serapeum is a temple of Serapis and the Royal Palace. Some were special collections with limited access, e.g. for priests or royalty, and a recent expert, Casson, says at its height it had about 700,000 roles. So I'll say a little bit more about a roll a bit later on. As a digression, it's a roll, it's not a scroll. And to help you remember, it's a Rolls Royce, not a Scrolls Royce. That's the one joke I have for this talk. But who knows, there might be another spontaneous. To give you another context about the city of Alexandria, here's a rather fine map made in the 19th century, which is a little bit speculative because the whole of the city is covered with modern buildings now, and it's not accessible anymore to archaeologists. So to give you some sense of where we are, sorry, I just lost the image there, but we're back again. To the north of the city is the Mediterranean. We're in Egypt. We're at the northern end of Egypt in the Nile Delta. There is a saltwater lake down to the south here. In the middle, there's a spit of land going out to the Pharos Island, which is famous for the Pharos Lighthouse, built at about the time that we are in the 3rd century BC. And the causeway that connects the mainland to this island was built by ancient Greeks, and it's still there underneath buildings. And in this map, there are buried in here, you have to look very closely, there are indications of where it is thought the royal palace was, over here, and the museum and the Serapeum somewhere down here in the western part of the city. By the way, do interrupt if you want to ask any questions. So I'm going to say a little bit more about the library now. And there is a mathematical problem that one needs to think about. Suppose you have never been in a library before and you've never had 700,000 rolls to order. There's a problem with cataloguing and what to do with the collections. And the librarians, they had to solve two problems. Like I say, how to order all the rolls on shelves and how to catalogue them. And it may come as a surprise to you that it was as late as this, 2nd, 3rd century BC, that alphabetical ordering began in a big way with the library catalogue. And the first director, who it is recorded is a philosopher called Zenodotus. His work on alphabeticizing the collection is recorded by the poet Callimachus, difficult one to pronounce, but I'll have a go. And he wrote these things called pinakes, which survive in fragments as evidence for what kind of cataloguing that they were doing. And he listed alphabetically, for the first time, authors' names, where they came from was included in the name, what works they'd written, and the shelf marks where to go and find them. And these were cross-referenced, so there might be several entries, depending on what the author was doing. If they were working on several topics, then there will be several entries. And the organisation of this knowledge helped to stimulate scholarship so that experts could come into the library and find where these different items were. And it may come as another surprise that punctuation had a liberating beginning with this work of cataloguing items, as well as literary comparison, criticism, and between texts there are comparisons, e.g. if you have a collection of maps which all claim to be maps of Egypt, which are the best ones? If you want to write a new one, what sources should you use? And if you're a doctor, you don't want to prescribe a deadly plant, so you might need access to a reliable pharmacopoeia where it's illustrated with reliable pictures. Sean?
So this is where alphabetical ordering started?
Yes.
Was the alphabet not in an order before? Did they invent the order of the letters in the alphabet?
Well, it's one of the strengths of the Greek alphabet, that it is a well-structured item that you could build an alphabeticizing on.
But the order of the 24 letters could have been in it.
Yes, but even at that time it was...
Was there already a standard order for the 24
yes,
letters?
alpha, beta, gamma, yes.
Definitely. Okay, that exists already.
Yes. Thank you. So not much is known about the physical arrangements of Alexandria. Like I say, it's all under the modern city. But at Pergamum, there were quite extensive archaeological digs, and there's much more evidence about how the library there was arranged. Basically, it was 3 storerooms and 1 large reading room, and the dimensions of the reading room are different in dimensions to the size of a papyrus that might have been stored in the library at Pergamum or in Alexandria a little bit later. So I'll just leave that there for you to have a look at. So that's not quite 10 meters. I'll say a little bit more about rolls in a minute. So one of the limitations on designing a roll is that its width of about 30 centimeters, about the height of an A4 sheet, is the length of the grass from which papyrus is made. The papyrus material is made from reeds of this grass. So you're kind of stuck with that dimension, but the length can be pretty much whatever you like. Let's see if I've got everything on my slides sorted. Yeah, 81,000 for one room, so something like 4 times that for the library at Pergamum. So the reported number of rolls available by the sources, the historians, is not just wild, this is plausible for those buildings. So here's a little bit more about rolls. And like I said just now, the height of the roll is dictated by the 30 centimeter height of the grass stems from which papyrus is made. And these sheets were written on like modern A4. So each of these sections that I made for this facsimile are like A4 sheets, and they're glued together in this section. So if you see in a movie someone reading from a scroll like this, they got it wrong. It should be like this, with the two halves, the two pieces in your hand, so that you can comfortably read it. And a little footnote to this is that around about the 1st century AD, the codex became the prime format of books. And a codex is one with a spine, as we understand a book today. And gradually, over several centuries, the codex became dominant. Now I want to talk about mathematics, because I've been spending my time about Alexandria and the setting of the library. Euclid is thought to be the first mathematician drawn to the library at Alexandria, and he was tempted by possibly wage, the chance to teach, and facilities there that would have been quite wonderful. Nothing is known about Euclid. We don't know where he was born or even where he was trained. It's a guess that he might have been trained by followers of Aristotle in the 4th century BC, but it's just not clear, not recorded. But Euclid is famous for his work, The Elements, and a few other minor books which need not be mentioned in this talk. The Elements is the real foundation of his fame. Yesterday I counted up that there are 465 propositions, theorems in his Elements in 13 books, and they're all proved, along with other material. So Euclid is an example of a mathematician working in a place, attracted by the money of Ptolemy and facilities. Very nice. Alexandria was a genial place to work. Ptolemy's attracted scholars to do research and teach. For example, locally, from Africa, in a place we now call Libya, in Cyrene, Eratosthenes of Cyrene was drawn to the library, and he was one of the librarians, chief librarians. It's thought that he was the 3rd one. And he estimated the diameter of the Earth extraordinarily accurately from a nice argument that's mathematical. And it's nice to reflect that astronomy, as today, is a wonderful stimulus to applied mathematics. The 3rd example of someone in Alexandria thought that Archimedes visited, and certainly knew people in Alexandria. Archimedes was based in Syracuse, in what is now Sicily, as we call it. It's thought that he visited at some time when he was quite young. He certainly knew Eratosthenes because it was discovered in about 1900 that he dedicated one of his works to Eratosthenes. So they certainly knew each other. A little bit more about mathematics. I've already mentioned some of the figures on this list of mathematicians, which is in chronological order. Euclid, Archimedes. I'll put a question mark because how long he spent in Alexandria is not clear. Eratosthenes, like I say, the 3rd librarian. Apollonius of Perga deserves to be better known because he wrote one of the first monographs on mathematics in the sense of a research item which was aimed at fellow experts, and it really is a fantastic piece of writing. I recently got hold of a reprint of his work on conics, and it contains wonderful material. Unfortunately, of the 8 books on conics, only the first 4 survive in Greek. It's a lucky survivor for the 5th, 6th, and 7th books that Arabic translations came to the fore, and the 8th book is lost entirely. It's been reconstructed, but it's all guesswork. Hypsicles, properties of regular polyhedra. He was working in Alexandria, and he tried to have some of his work made more famous by slapping on an extra chapter to Euclid's Elements. It's the 14th, so-called 14th book of Euclid's Elements. It's actually by Hypsicles. Heron is better known, certainly amongst engineers, because he wrote on mechanics and fluids and other topics of great interest to practical, what we might call engineers or scientists. Menelaus, you may have heard of Menelaus' theorem, I won't dwell on it. He wrote on Spherica, to a theory of spherical geometry, mathematics stimulated by the study of the stars and movements of the planets. Ptolemy should be better known amongst mathematicians because although he's famous as an astronomer, if you read his Almagest, or Almagest, first 3 chapters are loaded with what we would now call primitive trigonometry. This was something new in about 150 AD when he was around. It's really rather mathematical work. And very good. It's called Almagest because Arabic translators thought it was absolutely wonderful. The greatest, I guess, is what Almagest in their term meant. Diophantus, better known to number theorists, so problems with integer solutions. His work, Arithmetica, is available today in reprint. Pappus, a little bit obscure in his own right, but he's well known amongst historians because his mathematical collection contains a vast amount of material where he quotes and reports on other people's earlier work. So if it wasn't for Pappus, we wouldn't know about Archimedes' work on semi-regular polyhedra, for instance. That work is lost, but thanks to Pappus, we do know about his and other people's work on mathematics. A little bit later, so we're coming down chronologically here, in the later centuries of Alexandria, Theon, really an astronomer, but he's famous because of his, because he was father of Hypatia. Forgive me for the pronunciation again. I don't know what it is, but Hypatia, famous as very late antiquity female lecturer, public lecturer and teacher in Alexandria up to the time of her death. And other people as well. These are just the more famous mathematicians working in Alexandria or who have an Alexandrine connection. Sadly, I have to talk about the decline of the library because over the centuries, it got a lot of damage. Julius Caesar started the trend in 48 BC when he was invading Egypt, and a lot of books were burnt. It's not clear from the sources exactly how bad the fire was, but it was bad enough. Plutarch and others report on the things that were going on, but Plutarch was writing much later. Mark Antony offered Cleopatra 200,000 rolls. I don't know whether that's a romantic gift or what, but he did offer, and it's thought that there must have been a library still there for her to receive such a large gift. And much later, when we're getting into the 3rd century AD, large-scale damage to the library took place during a civil war, and the Romans were fighting against Queen Zenobia in a period of great turmoil. I mustn't digress, it's a very interesting time. And further decline, But we're approaching the 1 equation, so if you like equations, there will be one in a minute. In the Roman Temple of Serapis held books. It seems odd these days to have books held in a temple, but it was a secure place to keep them. And it was destroyed by order of Emperor Theodosius, who was one of the first Christian emperors, and he wanted to suppress the earlier religions. The museum, another building, continued as the center of scholarship in Alexandria. Now, Hypatia was the last known mathematical researcher there. She and her astronomer father, Theon, edited Elements and Ptolemy's Almagest during that period. In 415, Hypatia was murdered by religious fanatics, and do take the time to see, if you've not seen it, the movie Agora, very fine reconstruction of that time and that era. And it does some justice to the mathematics of that time too. The library's last manuscripts may have been stolen, burned, or sold off, And Alexandria did continue, at least as a centre of study, probably under private tutors. Another point in time is that rather later, in 642 AD, Egypt was occupied by a Muslim army, and Islamic research began there, especially in medicine and astronomy. And we have a great debt to Islamic scholars for being curious about translating and writing scholarly editions of the Greek works that came before them. There is no evidence Arabic armies burned the books. That's a myth. New centres of book copying and teaching grew up not only in the Arabic world, but in Antioch and especially in Constantinople. That's the Byzantine Empire, if you like, where the Greek and Latin languages continued. So here's the equation I promised you. This is a model of what happens to books when you don't copy them. And it goes like this. Suppose you have one work, Archimedes' Parabole, and you make lots of copies at the start. Over time, you'd expect the number of copies to be lost or burnt or eaten or whatever. So this model is saying, let's suppose that every century there is a number, a constant d, which is positive, associated with a decline. And it's multiplied in this equation here by the number of extant books. N of t is changing over time, and in the same way, as each century goes by, we're going to suppose that there are a certain number of copies made. And I've modelled this so that the number of copies per century is a constant, independent of the number of copies that are out there. If you are one scholar, you might make one copy for yourself. It's got nothing to do with the number of copies that are out there. So this very simple linear model is a differential equation, which says that the rate of change of the number of copies over time depends on two terms, a declining term minus dn, and a constructive term, c for copying. And the solution of this differential equation is n of t, and it's a constant c divided by d, and then another constant, n naught minus c over d, or multiplied by an exponentially decaying term, e to the minus dt is going to tend to 0 as t increases. And I've introduced another constant there, n naught is the number of copies which you make at publication date. And in my example here, let's suppose we have 1,000 copies. That's not an unreasonable number for a professional scriptorium in Rome in the 1st century AD. They could make 1,000 copies with slave labor to help. And I've just guessed a number, that the destruction rate 1, and I'm supposing that just modestly, every century, just 3 copies are made of, let us suppose, Archimedes' work on Parabole. What would we expect to happening over time? And the model says that the declining term over here, the exponential decay, kind of wins, and you only need to wait only 7 centuries for this term to be effectively nothing. And you're left with the first constant, c divided by d. You see in here, the bigger you make the destruction rate, the fewer the number of copies c divided by d you have. But if you are actively participating in lots of copies, then c divided by d is going to be larger. There's a competition between natural destruction and the efforts of copying. And if you don't copy, then you're not going to have any copies left. Ultimately, that exponential will always win. So n tends to 0 when c equals 0 is the other numerical example I've got on this slide. So there, I fulfill my promise of having one equation in a maths seminar. And it happens. The complete loss of works does happen. I mentioned Archimedes' work on semi-regular polyhedra. It's gone. Absolutely vanished. No copies, not even fragments left. If it wasn't for Pappus, we wouldn't know about that work at all. So that's the end of topic 1, where I've told you a lot about Alexandria. It's a wonderful place to work and a sad decline over several centuries. The second topic is to do with how ideas have funny starts. And I'll pick up a little bit in the later parts of this topic, how ideas turn into mathematics and get transmitted. So it's a rather murky story that begins with an architect called Filippo Brunelleschi back in the 14th, 15th century in Italy. And he had some ideas, spoken ideas, discussed with other people about how to paint paintings that look realistic, with proper perspective. Proper in the sense of Western views of art. And Masaccio, I hope that I pronounced that right, Masaccio, in the 15th century, had examples of the first paintings in perspective. I'm going to show you a couple of examples of his work. In fact, let's look at Holy Trinity Church, Santa Maria Novella in Florence, this painting from about 1425, which has a vanishing point in it. So here it is. I hope you can see that, all right? This is a work, which is obviously a religious work in a church. It's rather large, several meters across, many meters high, and it's set up on the wall for a visitor to view. And this was shockingly new at the time because it is in perspective. And the first thing that might catch your eye is the barrel vaulting on the top of the picture. And it's set in an architectural frame, but the barrel vaulting, the ceiling that's up here, is quite convincing. Further down, we have a sense of using a space to give you a sense of looking up, and I'm seeing something large and grand and important. So God is up there. God is portrayed in this blue gown, and he's right up there in the top of this space, this chapel-like space. And further down, we have the Jesus of Nazareth on the cross, and his head is the position, approximately, of the vanishing point for this picture. It's the place where Masaccio wanted the viewer ultimately to be coming back to as you look at the painting. Further down, we have Virgin Mary. I don't know who the person on the right here is portrayed, but interestingly at the bottom, we have two figures, extreme left and extreme right. These are the married couple who paid Masaccio to have this painting made. So it's an interesting document, even though it has no equations or words in it. It records a moment in time, 1425, when it's thought that perspective began. Here's another painting by Masaccio, somewhat better preserved. And here you can see that he's a master of dramatic tension, as well as just using perspective. The architecture on the right of the image is a house drawn in perfect perspective. And we're all convinced that this is a space that has depth. It's obviously a view of three-dimensional space. And the drama is coming from noticing, for example, most of the figures in this painting have heads at about the same level. That's correct. In a group of people who are about the same height, you'd expect the eye lines for all of them to be about the same level. The figure off to the extreme left is obviously crouching and further away. Again, that gives you a sense of, oh yes, there's a back to this group of figures. There is a sense that you can go with your eye looking further and further back into the landscape and the mountains in the background. And the vanishing point for this picture is on Christ in the middle here and at his head. So again, the artist was trying to get the viewer to focus on the most important central figure in this story. This is called the Tribute Money, by the way. It's a very beautiful painting, I think. So far it's been practice, artists, particularly Masaccio, getting the ball going with perspective. First person to write down a recipe or theory of perspective was Leon Battista Alberti in the early part of the 15th century. He wrote two versions of one painting, one in Latin and one for practitioners and one for scholars. And he was himself an amateur artist. So rather than going through that early slide, just tell you what his recipe is. So there's no real mathematics here. You're an artist, this is what you do if you want to make a convincing painting with depth. There's a vanishing point in the upper part of this. He describes a square panel, but a rectangular panel in this diagram, and a horizon line. And on the bottom of the panel, just mark off in brachio, or feet, equal divisions along the bottom line of the painting, and use these as points of radial lines that are drawn from the vanishing point down to the bottom here. And the problem that he solves is where to put the horizontals in this. Ultimately, we want to wind up with what looks like a floor arrangement of square tiles. You can do it by looking at the left half of this diagram, where we see a viewer at the correct position with the eye on the horizon line. And in this case, he is looking along the horizon line towards the vanishing point, And these radial lines that come from the eye of the beholder are drawn down to these marks, which you put earlier along the bottom of the panel. And this allows you to get the right spacing for the horizontals so that they are receding towards the horizon line, at exactly the right level. So this is the recipe you follow to get a painting with the vanishing point and some true perspective. It's certainly a good start because the square floor tiles give you, in some sense, a distorted coordinate system on which to put objects and give them the right heights. Now, here's some words to remind me of the bits and pieces. Mantegna, in the middle of the 15th century, was also looking at perspective and trying to draw quite dramatic paintings, and he too was interested in work in churches. So this example I'm going to show you is St. James being led to his execution, and the vanishing point is interestingly below the bottom of the picture. Let's have a look at that. I'll explain the picture. St. James is being arrested, and he's over here. He's second from the left, and the other figures here are mostly soldiers. And if we look up at the top of the picture, we see some very heavy architecture. It looks top-heavy. And if you look over here, there's a bit of sky, and the sky is entirely black, certainly very dark. It's an oppressive, rather depressing picture, which is right for the mood of St. James about to be arrested. So what's really dramatic about this picture is this sense of weight coming down on the viewer, is that we're below the level of the street in this street scene. We're looking up at all of these figures here above us, and Mantegna has even put in two of the soldiers and feet which are sticking out over the front of the panel. So we see the underside of the heel. It gives this very strong sense of drama, all brought about by true perspective. It's very sad that this painting no longer exists. It was destroyed in the Second World War.
Picture of it that has that. Do you know how we got the picture on the slide?
This is high quality photograph taken before the war, so we're lucky. Yeah, it's a kind of survivor. This is anonymous, but an extraordinarily beautiful panel. We thought it might have been part of some furniture, and it's guesswork about which painter in about 1470 put this together, and other related panels. It's mysterious because there are no human beings in this. It's purely architectural study. But you can see these images on the net if you Google ideal city. And it's just another example of perfect perspective at that time. I've got a couple of slides which I hope to have time to show you of Leonardo. Ah, good, yes. So Leonardo, 1470s, very interested in mathematics. And in this sketch, preparatory sketch for the Adoration of the Magi, which is an unfinished picture, he's made a lot of efforts to draw a floor with hundreds of lines, both correct horizontals and many radials. If you look closely in there, and you'll see he's inked in all these panels, or these squares on the floor, before he started on any of the architecture, let alone all the animals in this picture. If you look hard, you'll see a camel, some horses, and some human figures as well. It's really quite intriguing what was going through Leonardo's mind when he was planning out his painting. This is just a preparatory sketch. Another Leonardo here, well, it's a woodcut in a book, and the design is attributed to Leonardo. And it's rather interesting, 72-sided solid has a feature that it's a skeleton. You can see through the faces so that you can have a feel for the structure of the solid in the back as well. It's thought that Leonardo made models to help him draw these sketches, but it's a really wonderful example. It has a mathematical connection in the sense that Leonardo was working with Luca Pacioli in the latter part of the 15th century, and there was a delay when before this book by Pacioli, called, the book is called De Divina Proportione, and it was published in Venice in 1509. And it has lots of wonderful woodcuts in it, like this, all designs by Leonardo. So there are no mathematicians on the scene until Desargues, quite a lot later in the 16th century, takes an interest in the mathematics of perspective and progression. He was living 1591 to 1661, a long time ago. His most important work was printed in Paris in 1636 under the extremely modest, quiet title, a rough draft for an essay on the results of taking plane sections of a cone. And it consists of 12 printed pages, 50 copies were printed for his private circulation. They were all lost. And then remarkably, a manuscript copy of the printed text was discovered in 1951. So without that, we might not know about this early printed work. Desargues defines a pencil of straight lines in three-dimensional space. He considers points at infinity, line at infinity, all these modern ideas of perspective mathematics, and unifies all the conic sections as projectively equivalent to each other. He shows which properties of line segments are invariant under projection from one plane to another. So this is the mathematics underlying making proper pictures as we view them in the West. So it's a story of rediscovery, because later history of Desargues' work is a lesson in how ideas can repeatedly fail before they finally gain recognition. An artist, mathematician, Peter Philippe de la Hare, in the following century, read the posthumous manuscripts of Desargues, and in his own book, in 1685, he wrote a conic sections, published describing some of Desargues' work, including Desargues' theorem, which I'll come on to in a minute. The work of de la Hire and Desargues was later appreciated, another delay, another generation, and picked up by Gaspard Monge and his pupils. And then there was another delay and another rediscovery later in the 19th century by Michel Charles and his followers, who really got a science of perspective geometry on a very firm footing in a modern sense that we understand it. And Charles was very generous. He took the bother to look back about who to give credit to. So his historical reviews are important even today. But just to think a bit about the mathematics of projection, just about everything changes when you project from real space to a flat picture plane. So you lose angles, lengths, proportions, distances. What is preserved? Practically nothing. Well, some things are preserved. Points are projected to points, and line segments are definitely still line segments. That's still straight. And if two line segments intersect at some point in space, at a point P1, then their projections are going to be intersecting as well at some point P2 in the picture plane. And another thing is that if you have a tangent to a curve, then the property of tangency will also be preserved under projection. All of these things come under Desargues' theorem, which is written out in its full 17th century glory here in modern notation. I won't dwell on it because it's a bit fiddly, so I'll just show you the picture that goes with it. This is my picture. What I've tried to do is to convey a sense of what a projection is. So you can think of these two leaves, or planes, pi1 and pi2, which I've put in an angled way. You can think of this as being an open book when we're looking at two facing pages, pi1 and pi2. And in this three-dimensional view of the world, everything's in perspective, there is a point E for I, at the top of the diagram, which is where your eye is. And your eye is effectively projecting rays out into space, and what you see is going to be drawn on a picture plane. So underlying Desargues' theorem is this notion, well, if I project a triangle, what do I get in another plane? So A1, B1, C1 is a triangle in the plane pi1, and as projected from your eye, it's going to be projected onto the plane pi2, and you get a triangle. No big surprise there. You get a triangle which I've labeled A2, B2, and C2. So points are corresponding to points, and lines are being projected onto lines. We don't suddenly get something curved. And Desargues' theorem is not just that, but it says that if you extend the edges along their planes, then they all lie on one line. And let me just highlight one of those. If you just look at the line segment A1, B1 in plane pi1, A1, B1 is an edge of the first triangle, if we extend it with the dashed line along to the point P, then it meets there the edge A2, B2 in plane pi2. It's being extended in its plane, and it also meets this plane at this point, P. And it has to, because there's nowhere else in this space where the two edges extended can meet. It has to meet on the spine of the book. Same for the other two edges. When they're extended, they have to meet up, and they meet at Q and R. What is the surprise is that P, Q, and R all lie on one line. They have to, because they're on the spine of the book. So that's Desargues' theorem in pictures rather than in words. So I now reach the conclusions, and I want to allow a bit of time for questions if there are any. What I've done is to try to show you some historical context by picking up the city of Alexandria and the library there, and some sense of the creativity that there was, so many famous mathematicians doing work and teaching there. And in times of war and decline, scholarship can stop, and I modelled that. No copies, no works left. And in the second part, my item 3 here, it's mathematical ideas are stimulated by decorative art and craft. So this is what I suppose we can think of as applied mathematics, often being stimulated by practical problems, how to paint a picture that looks convincing. These ideas are mobile, trades in not only in books, but also in paintings and drawings. How did you do that? That would stimulate a painter to want to learn about perspective. And also this tale of rediscovery in perspective is perhaps typical of ideas in mathematics, that it needs new audiences, new people to rediscover and reinterpret other people's ideas. So there I've traced in the history of perspective all the way from Alberti through to Charles. And that's about it. Thank you very much. The end of my talk. Thank you for coming.
Thank you very much, Mark, for a very nice presentation. We can forgive some of mispronunciation of Italian names, but
Big forgiveness.
yeah. Any question? The audience here online. Okay.
It's not exactly history of maths, but it's about perspective. About 15 years ago, someone became aware of sports events that they started putting advertising on that was designed so it stands out. So cameras from a fixed camera angle can see it perfectly. If you're on the ground, you can't. And there's no one you know whether anybody made large amounts of money from using perspective. I keep thinking, it's so obvious, I should have done that.
You should have done that, Paul. That was an opening bit.
But I just know whether you're sort of aware of that.
That's curious, isn't it? I wonder whether they were using ideas of traditional perspective to get that to work. I don't know about pinhole cameras giving you a very deep sense of field so that everything is in focus. Perhaps that was the trick.
Yeah, and it's perfect because they're using a fixed camera angle, so they know what the camera is, they're designing it, they print it onto the pitch. It looks weird when you actually at the ground because it's all distorted, but when you see it get on television, it looks perfect advertising.
Amazing.
I mean, it is possible that nobody made much money because the idea is relatively generic. It's the same idea as moonlighting.
Yeah, but it's just like whoever developed the software and sold it to grounds, they managed to actually make a
Yeah, rather than someone working out how to rip manually.
I have a question. Did you create that scroll yourself?
Yes.
Did you write it on this?
Yes.
That's dedication.
It's an Egyptian ruler as well. It's another talk, really. So I thought I'd bring it along in entertainment. It's marked rather cleverly. Until I made it, I didn't appreciate how clever this is. But ancient Egyptians knew a thing or two about practical things. So if you want to know more, then I'll be in the team.
What's the scaling on that book? Are they, presumably not inches?
These are not inches. These are fingers. That's a finger.
A finger. Oh, finger.
And that's a palm. Really nice little groove. And that's a cubit. A cubit, C-U-B-I-T, as in the Bible, cubit. This is an ordinary cubit, a royal cubit of be an extra 20% or so. So it's another talk, not question.
Yes.
Do you have any other questions online? Anything else? I think everyone wants to go and grab a coffee in S120 with some biscuits. Possibly.
Biscuits, nice biscuits today. Yes.
And yeah, I mean, like, let's thank again Mark for giving us.
Thank you.